Power of the turn. Physics of the tunnel boring machine. In the past, building tunnels required explosives and dangerous manual labor. Today, engineers use a massive machine called the tunnel boring machine, or TBM. This machine can weigh thousands of tons and drill through soil and solid rock deep underground. But how can such heavy machine rotate and cut through the earth? The answer lies in physics, especially a concept called torque. So, what is a TBM and why is it built? First, the tunnel boring machine, or TBM, is built as a large cylindrical structure. It contains a rotating cutter head, a working platform, conveyor belts, and cutting tools on the front. It is used to build subways, sewer systems, and underground roads, while causing very little disturbance to the surface above. So, now, the most important physics concept in the tunnel boring machine is torque. Torque is the turning effect of a force that causes an object to rotate about an axis. The cutter head of the TBM rotates to grind and break rock in front of it. The formula for torque is torque equals to radius times force. Tau represents torque. R is the distance from the center of rotation to where the force is applied, and F is the applied force. Torque depends on two main factors, the amount of force applied and the distance from the center of rotation. If either the force increases or the distance increases, the torque will also increase. In the tunnel boring machine, engineers design the cutter head with a large radius so that it can generate greater torque to break through hard materials. This is similar to opening a door. It is easier to push the door from the handle than near the hinge. A larger distance from the pivot produces greater torque. The same principle is used in the tunnel boring machine. The TBM must also move forward while cutting. This is done using a hydraulic system. High-pressure fluid is pumped into thrust cylinders that push the machine forward against the tunnel walls. This uses Pascal's principle, where pressure applied to a fluid is transmitted equally in all directions. This shows that the hydraulic system is important because without forward force, the cutter head would not be able to stay in contact with the rock surface. Both rotation and forward pressure are needed for the TBM to function effectively. Workers operate the TBM from a control room using computers and monitors. They monitor torque levels, pressure, speed, and direction to ensure the tunnel is safe and straight. As the tunnel boring machine moves forward, it does not leave the tunnel empty. Behind the cutter head, concrete segments are installed to form the walls of the tunnel. These segments are carefully placed and fitted together to create a strong circular structure. This process happens continuously as the machine advances, allowing the tunnel to build efficiently and safely. As the cutter head breaks the rock and soil, the excavated material must be removed from the tunnel. This material is transported through the machine using a conveyor system or slurry pipes. The system carries the soil and rock away from the cutting area to the back of the machine, where it is then removed from the tunnel. This continuous removal process ensures that the cutter head can keep moving forward without obstruction. The tunnel boring machine has many benefits. It is safer for workers, faster than traditional digging, and causes less vibration to buildings above the ground. It also installs concrete segments immediately to create smooth and strong tunnel walls. In addition, the use of TBMs reduces noise and environmental impact compared to traditional construction methods. This makes it more suitable for building tunnels in busy urban areas. Overall, the tunnel boring machine demonstrates how physics concepts such as torque and pressure are applied in engineering to solve real-world problems, making modern tunnels and subways possible.